Hello, my name is Lars. I'm going to present MinervaFS, a user-space file system for generalized deduplication. It's a collaboration between the listed authors from Aarhus University, Department of Electrical and Computer Engineering in Denmark, and University of Neuchâtel, Department of Computer Science in Switzerland. So the problem that we're trying to mitigate, not fully solved because that's impossible, is the fact that us humans and the machines we employ are generating and collecting data at a higher and higher velocity and at a higher and higher volume that has no signs of slowing down whatsoever, and it is estimated that by 2025 alone we'll reach an amount of publicly available data that will reach 175 zettabytes, which puts an immense pressure on our storage system, and since some of this data has to be stored persistently, this means stored without any data loss or any corruption whatsoever, we have to look at technologies that can reduce the amount of data we store without losing data. Now, there do exist current state-of-the-art technologies for this, such as compression algorithms, delta encoding or delta compression, that's the same thing, just different names, and classic deduplication. Now, there is an emerging technology called Generalized Deduplication, which aims to improve the deduplication ratio of classic deduplication, and that is the technique we have built MinervaFS around, just to test if it is possible to design a file system using this technique. Now, classic deduplication works by having original data, chunking it into some chunks, looking for duplicates, like looking for repetitive bit patterns amongst the chunks, even those already stored in the system, not just those who are being stored now, and only store unique chunks. Now, in this case, in this little example, we say that the color of a chunk describes its bit pattern, and we see that C1 and C4 have the same color, and therefore we store only C1. However, C2 and C3 have different colors, and therefore we only store them. Now, an important part about the comparison is actually that we don't compare the full chunks. The reason for this is that chunks can vary in size from a few kilobytes up to hundreds of kilobytes, and even for a few kilobytes, that is an enormous amount of bits you have to compare, so it is a bitwise comparison. To reduce the cost of this, we use fingerprint functions which generate unique fingerprints for each chunk. As an example, classic deduplication-based file system ZFS utilize SHA-256 to generate fingerprints for their chunks. They use a standard chunk size of 128 kilobytes, which significantly reduces the amount of bits we have to compare. Excuse me. Now, generalized deduplication is roughly the same, but we add this transformation state. And what the transformation state does is it transforms a chunk into a basis and deviation pair, where the deviation describes how the chunk deviates from the basis. And then instead of doing the deduplication over the chunks, we do the deduplication over the bases. Again, we employ fingerprints on the basis. Now, the purpose of this is essentially to achieve a many-to-one mapping, where we map many chunks to the same basis and then have the deviation, which is supposed to be small, actually be what we store the most. So in this case, we say that the shape describes the basis, so the shape of the chunk describes the basis, and the color of a chunk describes the deviation. So in this case, we have colored C4 differently than C1, and we can see we're still able to map to the same basis, so therefore we only store B1, but we have to store both deviations. However, remember in the previous example, C2 and C3 have the same shape but different colors, and we couldn't store them as same, so therefore we ended up with 3 chunks. In this new generalized deduplication, C2 and C3 have the same shape but different deviations, but we still only need to store B2 and not B3. One thing that is important to note here is that even though the same deviation appears multiple times, we actually store that. Another thing is that the transformation function can essentially be any function that can create the basis and deviation pair. In our case, we use Hamming because that has been proposed before by other researchers, and we use it. However, in a specific configuration, we use the decoding step of Hamming as our transformation function, where we see the original message as our basis, and the deviation is the error, so the single bit flip that Hamming is able to correct. And of course, the then reverse to reconstruct the chunk is that we reintroduce the error into the original chunk, and then we can reassemble the original data. Sorry. So how have we actually structured MinervaFS? Well, we have a MinervaFS fuse layer where we have a component that contains all the functions that an application needs to think that it's actually interacting with a real kernel file system, so any POSIX file system, really. So that would be, for instance, write, read, unlink, and stat as just a few examples. Then we have the transformation component, which chunks the data. It can also reassemble it, and then create the basis and deviation pairs or reconstruct the original chunks. Then we have the deduplication component that hash the basis and identify duplicates, both between the data that is currently being stored but also already stored data in the system. And then the data is passed down, both the deviations or the structures needed to map a file to basis and deviation pairs will be stored in a kernel file system. We have not handled this internally in MinervaFS. We have outsourced this to a kernel file system. In our case, it's ext4, but it could be any POSIX compliant file system, such as, for instance, XFS or Butterfs. For the data sets we have we have a satellite image dataset and a pan-sharpened version of this of the same satellite images, consisting of each 69 files and 1.3 gigabytes size for the first one and 3.3 for the last one. And then we have some VDI images, and for those of you who don't know what that is virtual machine images for virtual box, and we split them into 512 megabyte chunks, with a few that remain to be a bit smaller than that, and in total 420 files and a total of 671.21 gigabytes of data. So a bit of variety in the dataset. What we achieved with MinervaFS is actually quite remarkable, because we showed that compared to ext4 as the baseline, we were able to provide reduction across all data sets, and that is even more remarkable when you look at for the pan-sharpened and VDI files, where we are able to provide 19.17% and 63.53% reduction in storage space. ZFS is not able to provide any reduction in storage space. Now, that does not mean ZFS is not providing any deduplication ratio, which we'll see in the next slide for VDI files, but the reduction in storage or the deduplication ratio is killed by the scaffolding around ZFS, so linking bases to files and stuff like that. This makes the result for VDI files from MinervaFS even more impressive, because we actually provide a compression that is close to what gzip and xdelta provides, with the 69.72% and 68.82% respectively. And one thing that is to remember here is that the 63.53% reduction and the 2.74x deduplication ratio that MinervaFS provides is including all the scaffolding, and that is important in the next slide. So all in all, we have shown that MinervaFS is actually able to provide these significant reduction in storage usage, even for small data sets. One comment I will add to this slide is that for some reason SDFS, which is a deduplication-based file system, use significantly more storage for the two satellite images, and we are not quite sure why. It seems to be something with the internal structure in SDFS, but we have been able to reproduce it across multiple machines. And as you can see, for the for the VDI files, it's actually close to MinervaFS. So I was talking about the deduplication ratio for the VDI files. Why is this important? Well, in this slide I've plotted the deduplication ratio for the VDI files for all the systems that are based on deduplication or classic deduplication, in combination in some cases with compression. Now, we have also plotted ext4 as a baseline just to show that it is 1, 1, 1, 1, 1, 1, 1, 1, 1. Now, ZFS with just deduplication shows that it actually do provide some deduplication. Then why, when we look here, is there no deduplication? As I said, this is down to the scaffolding. Another thing we can also see here is that ZFS with compression LZ4, it is actually close to GZIP or SDFS, for instance. But with deduplication, the ratio is actually, the compression is actually worse, which is even confirmed here. As we can see, ZFS with LZ4 and dedup provides a lower deduplication ratio than just the deduplication version of ZFS. Why is this? Well, this is because of how ZFS does it. So it compresses first and then provides deduplication. This is actually bad for deduplication because the compression removes duplicates and thereby lower the probability of finding duplicates. Another thing we can see is that SDFS actually do compression of the chunks, but does it so does the chunking first and then compression, and achieves much higher compression ratios. Sorry, deduplication ratios. And the reason we have SDFS and SDFS opt is because SDFS is SDFS including all the is without all the scaffolding, and SDFS opt is with all the scaffolding. Another interesting thing is that we can see that, as shown in the last picture, that MinervaFS does provide the best deduplication ratio, but with compression it becomes even higher. And again, the reason for this is down to the fact that that we compress after we chunk, after we create the bases. And what is more important here is that the numbers for ZFS actually does not include all the scaffolding, where for SDFS opt and for both MinervaFS versions the scaffolding is included. So that is pretty significant gains. So, in summary, order of compression matters, and GZIP increases the deduplication ratio for MinervaFS because of the way we calculate compression deduplication ratio as including all of the scaffolding and stuff. And it is fair compared to ZFS because they don't include the scaffolding. So yeah. So what can we actually conclude? Well, what we can conclude is that we have presented the world's first file system based on generalized deduplication, and that we are able to create a file system based on this, which is pretty significant and pretty amazing. We have also shown that we can provide significant gains compared to ZFS, in particular for VDI files, where we provided 63.53% compression gain compared to ZFS and compared to ext4, and that we were close to GZIP by only using 20% more storage than GZIP. All while only using Hamming codes, meaning our deviations are representing 1 byte. So we have to map bases that are 1 byte different, right? Chunks that are 1 byte different. So that is pretty significant and pretty impressive. For future work, we would like to add, of course, more transformation functions, for instance, explore the application of Reed-Solomon, or come up with our own transformation functions, or use other transformation functions that have been developed by other researchers, and in particular also combine them with other generalized deduplication configurations, for instance, smaller chunk sizes, larger chunk sizes. As I stated, we have used 4 kilobyte. What would happen if we jumped up to 128 kilobytes as is used by ZFS? Then also, like compared to other compression formats, for instance Snappy, go into more details with, of course, performance evaluations of this compression versus generalized deduplication, like what is fastest to compress and then uncompress, or use generalized deduplication in the way we're doing it. Additionally, we also look at adding other compression algorithms to MinervaFS and see, is GZIP the best, or can we actually provide a higher compression gain by using another compression algorithm, for instance. And finally, one thing we would like to look at is at versioning, because versioning is one of these things that is always nice to have. Like, all developers love Git, for instance, or another versioning tool. And even Dropbox provides versioning of its files. So be able to provide versioning of different files, because the difference between different versions has the potential to be low, and therefore we expect to find a lot of duplicates across multiple versions of files, and therefore it would be interesting to investigate how generalized deduplication can be able to provide versioning at a significantly lower cost than providing full file copies, which is the customary in some systems today. So that is all for me. Thank you for your attention. Have a nice day.